Share screen. Okay, can you guys see the presentation right now? I think so, right?
Yes.
Okay, good, good. Thank you, Tommy. So basically, in this class, we're gonna talk about the extrusion-based systems, which is the most commonly used ones, like the fused deposition modeling. Actually, that is one type of these extrusion-based systems. So we're gonna have some more detailed discussion on it. All right. So basically, the extrusion-based system is quite similar to a cake icing, right? You all know what is cake icing, right? So basically, the material contained in a reverser, and then the material is forced out through a nozzle when pressure is applied, right? So as shown in this figure, so basically the material will be fed onto the substrate by applying certain pressure, right? So if the pressure remains constant, then the resulting extruded material will flow at a constant. So that is very important. So remember, when you do the cake icing, so you want to make sure the force you applied is a constant force, such that the result pattern will be good looking, right? Otherwise, it will mess up what you're gonna do for the cake icing. So that is a very important point for also the extruded-based additive manufacturing. And the constant travel speed of a nozzle corresponds to the constant flow rate. So that's another point. That is the movement of the nozzle. So you have the constant pressure, you have the constant travel speed of nozzle, and these two will give you the impact on the pattern you are generating. All right. So the material being extruded must be in a semi-solid state when it comes out of the nozzle, right? So for like the FDM fused deposition modeling, so the material will be like such as the ABS or PLA, and they are all those so-called thermoplastics. So it is melted to a semi-solid state, such that it could be extruded, right? And then this material must fully solidify while remaining in that shape, right? So that's another property for the material, and that's how you obtain the 3D shape, right? It must solidify and remain the shape you extruded there. So you can see there's a state transition, phase transition actually, right? So the material is originally to be a solid state, and then it is transformed to a semi-solid state, and then it will solidify and become solid again. So there is a phase transition involved in the whole process, and that's why this process you need a very good thermal control, right? So that is essential for the final shape you can obtain. How accurate, how perfect the shape you could have. All right. Also, the material must bond to the material that has already been extruded, such that a solid structure can be obtained. So you have the new generated layers still in the semi-solid state has to bond to the previous material in the solid state. So that is also very important. And the additive manufacturing machine must be capable of scanning in a horizontal pattern, right? So basically in the process, it is still in a layer by layer manner. That means the each of the 3D object will be sliced to 2D layers, and then the mechanism of the additive manufacturing machine must have the capability to move in the horizontal plane in certain tool paths. So, and that is what we discussed in the previous lectures, right? So we discussed a little bit about the tool path generation. And also it must be able to start and stop the flow of the material while scanning. So because when you finish one layer, you need to move your nozzle upwards, right? And then start another scanning. So in the control system or the mechanical system of the additive manufacturing machine, this must be achieved, right? And last but not least, it must the additive manufacturing machine must index upwards or move the part downwards, such that you could have your Z dimension created. So all these factors will affect this kind of extrusion-based systems. And let's take a look. But before that, let's have a review on the injection molding process, because as you can see, there are many points of injection molding are identical with these extruded-based additive manufacturing, right? Let's see how we have we could link the injection molding to the additive manufacturing. So for the injection molding process, so you have the basic process like first heat the plastic material to a certain temperature beyond the glass transition point. And then the material will be injected to the mold to create a fully enclosed cavity. And the plastic material will be shaped to the desired shape, right? And another important thing here is you have the pressurized material. I mean, that gives you the better quality of the product, because you have pressure applied on the material when injected to the mold. That really is I would say a much better way than just casting, and that will give you very stiff shape after taking out of the mold. So this is I would say a very unique feature for injection molding, right? And then after the plastic material injected to the mold, another step is the cooling, right? So the plastic material shape will be solidified, and they are kept in the mold until it's fully cooled. And then the mold will be opened, and the part will be ejected and cut from the material. And then next part will be made. So that's the process for the injection molding. And this is a kind of a typical a workflow for injection molding. You can see they have different units: the injection one part, the mold part, and the clapping part, right? So basically, it covers all the steps I described, and we can take a look at the videos such that you will have a better understanding here. Okay. Oh, I saw someone asking questions, right? Take a look. Okay. Oh, here, chat. Okay, I think, oh, it's nothing to do with what I'm talking about. Okay, let's continue. Yeah. Let me share the screen of this injection molding. first of all, can you hear the audio of this video?
I don't believe so.
Oh, what should I do here? I think I need to share the audio. Okay, let me share the audio. Share screen. This one. Share computer side. All right. Okay. How about right now? It's fine, right?
Yes. Yes.
Okay. All right. So as all you can see is kind of quite a standard process for the injection molding. All right. So you can see there's some similarity between the injection molding and the 3D printing. So basically, first of all, they all use the thermoplastic, and they all have the heat, the phase transition of the plastic, right? Also, injection molding has a certain pressure. Actually, there are high pressure applied onto the material. In 3D printing, the pressure may not be that high, but still there's some pressure applied onto the nozzle such that it can extrude the material properly, right? And so for the most commonly used kind of extruded-based method, the fused deposition modeling. So you can see here shows the illustration of the working principles, right? So it has a extruder header over here, right? It can move in the both horizontal plane, and it can be lifted in the Z direction, right? And also the plastic, thermoplastic or wax filament extruded through the small head, right? And the initial layer onto a foundation with a constant rate. So the first few layers is quite essential for the whole success of the whole printing process. And usually it's in the solid pattern. So there's no infill pattern because you really want to bond the material, the printed part to the substrate tightly. So usually the first maybe 2-3 layers will be the solid layers. And then the extruder will go through certain pattern. That is the so-called infill patterns or so on and so forth, right? And once one layer is printed, this printing nozzle will go upwards by the layer thickness, and then the new layer will be generated. Okay, let's watch a video again. All right, let me share screen. Okay. Oh, I'm sorry. Probably I put the wrong video on my slides. But anyway, I think all you have the idea of how the FDM machine working, right? So maybe we just skip the video. I think I put the wrong video here. I will correct it on the slides and re-upload a new version. But anyway, you get the idea of how a fuse deposition modeling system work, right? And so basically, there are some important points for the extrusion-based approach. First of all, it uses temperature to control the material state. And first of all, the thermoplastic will be liquefied. And then it flow out through the nozzle. And then the material bond with the adjacent material before solidifying, right? And another point is it uses a chemical change to cause solidification. So there's a cure agent and a reaction with the air. And it's just like a simple drying of wet material. So all these 1, 2, 3, 3 different ways are the possibility for the a material be solidified during the printing process. And but the common point is there's a chemical change to cause this solidification according to what material you're talking about. But most commonly one will be the this just a simply drying of a wet material, right? That is, I mean, most used for the fuse deposition, right? Modeling. And some basic principles. So how to load the material, right? And in most of the systems, people just use the filaments, right? The material will be formed into some wires, and a certain mechanism will load the wires, the filament, to the heat unit. And then the heating unit will melt the material into the semi-solid state. And then the nozzle, through the nozzle, the material will be put onto the substrate and generate the shape, right? And so this, as I mentioned, the second step will be a liquefaction of the material. Once the material is loaded, it has to be melted, right? And then the third step is to press the material through the nozzle such that it can be extruded onto the base. And so another very important point is you have to plot the pattern according to what you planned for the tool path, right? And again, the material bound to itself such that this layer by layer accumulation of material could be achieved. And another thing is the support materials, right? So support structures actually. So for those complex geometry features such as overhanging and undercutting and so on and so forth, I mean, in one word, if the geometric feature cannot support itself, right? Due to the printing direction is the upwards against the gravity. So there are some geometric features it cannot support themselves. They cannot support themselves. In that situation, you have to print actual support material to support that. So all these factors will be essential for the FDM printing successfully done. And for the material loading part, so basically there are two important things. The material has to be preloaded, and you have to have a continuous supply. So such that people are thinking about to use a filament and a rolling mechanism to feed the filament onto this to the heating unit and the nozzles, right? And for the liquid, once the material is converted to the melted states, then certain pressure has to be applied to sorry, to put onto the substrate, right? But also there could be other options in some of the process other than just a solid material. It could have a unit material, right? So for the, the liquid material. So for the liquid ones, you have to design other mechanisms than those rolling wire mechanisms, such as the pumps, right? Because it's liquid. You have to find a way to fit the material. So that's why there are other mechanisms for the material loading. Even for the solid materials, other than just the filament, you will have other like the pellet or powder. For this kind of thing, well, you probably need to use other mechanisms to fit it, right? Like the school plungers or compressed gas and so on and so forth, or just use the gravity. I don't know. It could be options, but for most of the case, for most of the solid material used in the fused deposition modeling, it's in the form of the filament. Right? That helps a lot to simplify the mechanisms of feeding. And in the liquefaction process, so the material solidifies following the extrusion. So here shows a kind of illustration of the whole process, how the solid material is liquefied through this liquefied chamber, and then it goes through the nozzle, right? And then the material is extruded onto the platform. So the material actually is liquefied because the heat applied to the chamber. And that's why the thermoplastic is the most commonly used material. So under certain heat, above certain temperature, those thermoplastic will be melted into this semi-solidified state, right? And actually, this heat unit is kind of realized by using the heat coils wrapped around the chamber, and that will simply heat up the material and melt it. So the extrusion, in the extrusion process, the extrusion nozzle determines the shape and the size of the extruded filaments. It's just like a mold, like in the injection molding, right? It's quite similar to the injection, the mode of injection molding. So if the size and the shape of the nozzle is different, then what you have, what's to be extruded onto the substrate will be totally different, and that could affect final geometric features or the material properties of the products you printed. And the diameter of the nozzle also determines the minimum feature size that can be created. And in the later slides, I will show you the whole family of the nozzles with all different diameters, right? and I mean, you can obviously, if the nozzle size is bigger, you will have bigger feature size, and the smaller, you will have smaller feature size. But still, you need to balance the feature size versus the printing time. So if you choose a too small nozzle, probably you will need more time. So that's the price you have to pay, right? And material will flow through the nozzle. Actually, is controlled by the pressure drop between, I mean, the pressure drop between the chamber and the surrounding atmosphere, right? So how fast the material flows through the nozzle is controlled by the pressure. Another thing is the moving speed of the nozzle, right? So, but that's totally different features for this extrusion nozzle, and we're gonna talk about later. And in the solidification process, the liquid material should be solidified to remain the same shape and size, right? And the gravity and the surface tension may cause the material to change shape. So, well, that again, you have to decide how many, I mean, how many material you want to extrude, and that is controlled by the pressure you applied to the material flow, as well as the size of the nozzle will affect how much the material will be extruded, right? So there must be some principles, and those manufacturers of the FDM machine, I believe they did a lot of tests and try to find some optimal solutions for these like size and pressure to apply on the knob. And cooling may cause shrinkage and distortion, and that is, I would say, quite common for those thermoplastic material, right? So there always shrinkage and distortion for thermoplastic material when the cooling process. Also, the cooling process is nonlinear. It can be minimized by minimizing the temperature differences between the chamber and the surrounding atmosphere, and ensuring the cooling process is controlled with a gradual and slow profile. Because although there are some fan, right, on the printing nozzle, there's some fan over there, but still there's no other cooling cooling channel or something like that to actually cool the material extruded. So basically it just what actually cool the material is the surrounding atmosphere. So if the temperature of the material to be extruded is too different from the surrounding atmosphere, that could cause problem. So that's why those manufacturers will always suggest you some kind of ideal room temperature for you to install your additive manufacturing machine. But for some of the machine, basically they have a kind of a closed space for this process, and that could be controlled by the machine itself, like those high-end FDM machine. It's not just I mean, the material extruded will not directly interact with the surrounding atmosphere. So it is placed in somewhere closed, right? So in the machine. So that will be a very good kind of a setup for the machine to control the surrounding area. Surrounding temperature, and that could improve the quality of the printed products. But for the most for most of these kind of consumer level ones, you have to cool your printed layers by interacting with the surrounding atmosphere. Another thing is the positional control. So the platform index is in the vertical direction. So it controls how much the nozzle moved upwards or downwards, right? And the extrusion head is typically carried on a plotting system that allows movement in horizontal. Okay. So once the nozzle moves to certain certain Z level to print one layer, the nozzle will moved in the horizontal plane for this layer. And this plotting must be coordinated with the extrusion rate to ensure smooth and consistent deposition, right? And a change in direction must result in deceleration followed by acceleration. The corresponding material flow rate must match this change, or else too much or too slow material, too little material will be deposited in a particular region. So actually it happens to most recent machines. So in order to compensate this kind of too much or too little material extrusion, before they do the actual printing, they will find somewhere and just let the nozzle prepare. So they will extrude a small amount of material onto somewhere, and then they after this they will move their printing head to print the actual layer, and that gradually, significantly decrease the chance to have a messed up layer because of this deceleration and acceleration in the printing process, right? So the linear driven mechanisms like belt drive or lead screws need to be powerful enough to move the printing head and be responsive to permit rapid change in direction change without backlash effects. So yeah, that is why for some low-cost 3D printer, fused deposition printer, the printing quality will be pretty low because, well, to save their cost, they just used some cheap motor or belt, and it turns out it cannot control the motion quite well, and there will be some distortion generated to the printed layers, right? But actually, I will introduce you some other variations in fused deposition modeling, and in these systems, actually that could be some fully three-dimensional motion instead of first move your printing head only in the direction and then do the horizontal motion. For some of the delta-based delta mechanism-based 3D printing, it can it can actually move from arbitrary 3D point to another 3D point within the printing space. And I will give you some ideas about that later on. All right, let's move on. So another few points about the positional control. So as you can see, for each layer, there will be a outline or the contour, and then there will be the infill, right? So when draw the outline of the part, the nozzle used to move slower, such that to make sure this contour to be printed precisely, right? And but for the infill, basically it just inside. I mean, when the printing is done, all the infill actually is inside the three-dimensional object. So when printing the infill, usually the nozzle will move more rapidly, and to gain some efficiency for the printing, and obviously you don't need as precise geometric. I mean, as precise feature as the outer layers, outer lines. So that's why you could gain some efficiency by speeding up this infill printing. So if we talk about the bonding between each layers, so for the heat-based systems, the sufficient residual heat energy is needed to activate the surface of the adjacent regions, causing bonding. So when you finish one layer printing, there's still some residual heat over there. So after you start printing another layer, this heat energy could be used to bond the newly printed layer with the previous layer, right? So if there's some efficient energy, that will result in a distinct boundary between newer and the previous deposited material, and that will be some unpleasant features like crack, right? If the two layers cannot be bonded well, there could be a gap in between, and even cause the whole 3D object be cracked. So that's why you have to make sure there will be enough residual heat energy for each of the layer. But how about the first few layer, right? For the first layer, because there are no previous layer, right? You have to bond your first layer onto the printing substrate. So usually a typical way to kind of help the bonding is basically some heat unit is attached to the substrate. Usually, I mean, for the most of the commercial available ones, they use like glass as the substrate. So they use heat unit and to generate some heat onto this glass substrate, and that helps the bonding between this glass substrate and the thermoplastic material. That's how they handle this bonding problems for the first few layers. All right. But if you apply too much energy, that might cause the previous deposited material to flow, which turns out to generate a very distorted shape, right? So there you have to select the, I mean, you have to control this energy very well, and to make sure the residual thermal energy is not too much and it's not too little. So that is why the temperature control or thermal control is very important for the fused deposition model. And another step is the support generation. I think we have discussed a little bit about it, right? So, and there are different support material used for fused deposition modeling. One is the similar material supports, right? Or even just use the same material as a support. So if you are talking about the same material or similar material to be the support, then the bonding between the support and the actual printing part will be quite good. So because they are in the same, they have the same mechanical and chemical properties. So when you finish the printing and you want to remove all the support material, that could cause problems because it bound too well. So you have to kind of, in the design stage, carefully design and place with respect to each other, such that they could be separated at easily at a later time. So it's desired to just place the support material to those regions which are not which has no little geometric features, right? Otherwise, after you separating the support with the print part, you will damage the surface of the 3D printed part. So that's undesired. And also the fracture surface effect caused by adjusting temperature can be used to separate support from the part. But that really depends on how different the material you used to support versus the printing material. And if you use the same material, is really this kind of a way is really difficult to use for separating the support. But for the different material as the support, so as they have different mechanical property and different chemical property, so it's much easier to separate. And for some of the support material, those most recent 3D printer use, they can be water soluble. Means after you finish the printing, you just put it into water, apply certain heat over there, and after some time, those support material will be melted into the water. So that will be the most convenient way to separate them. But again, it's still a big waste if you print support material. It's big waste in terms of time and material. And well, if there's some way to avoid those support material, definitely that brings value to the additive manufacturing process. Another new development of fused deposition modeling is, right now there are some printer which are capable to print multi-material by extrude different material using different nozzles. Like the new Ultimaker 3 machine, it has dual nozzle. So two different material could be extruded in the single printing process, right? But again, you have to make sure these two material could be bonded well, right? So that requires some adjustment on the temperature, on the extruding rate of the nozzle, and so on and so forth. Also, there are some more advanced machines. They have more than two printing nozzle, and such that they could have the capability to print even more types of material in single printing, right? So the parting of the path control is essential for the additive manufacturing printing process. So as I mentioned, for the outer layer, usually lower speed is used for the plotting, and there's a stop and start location for this outer layer, outer line printing. For the interior printing, it usually to be faster, and basically it requires an offset inside the outline. So as you can see here, these patterns will not touch this outline. Why? Because what you actually, what the nozzle actually extrude here has the width, right? So that's why the tool path will look like this. But when the nozzle move and extrude follow this tool path, these regions will be connected because there's a width for the material extruded onto this the planar layer, right? And also different patterns could help to distribute the strings. As I mentioned, there could be some optimization work done there to decide what kind of pattern will be the optimal one for certain kind of mechanical property. And here shows the here shows this the pattern for the tool path versus the actual printed patterns. So this dashed line shows the actual tool path, and the solid line shows the deposited material boundaries. So you can see it's kind of an offsetting pattern of this actual tool path planning due to what I mentioned. There are some width for the material extruded on the three-dimensional on the plane. So you have to do the offsetting process to predict what kind of material will be over there when you just have this actual tool path. So here, basically, you have there are some overlapping of material, and that will cause some problems, because if these two regions are overlapped, that means there will be more material extruded there, and the thickness will be different than other region. So that could cause some failure or unwanted distortion. So you have to properly design your tool path such that the actual material will be properly placed and no overlapping. Right? So for the for this kind of tool path, there could be different ways, like this contouring patterns or those staircase patterns. So for those for this continual patterns, as you can see, this outline is the first layer to print, and then the interior patterns will be printed one by one. And you can see basically for one layer, this point will be the start point, and then go all the way back, and then move to inwards, and then start this plotting again, and so on and so forth until it goes to the most interior region. So that's how this contouring works. But for this staircase, so basically for the outer line, it's same, just I don't know, probably from here, right? So the outline will be printed all the way starting with this point and then come back. And then starting from this point for the interior ones and go with this zigzag patterns, and then all the interior ones will be printed. So there are a lot of tricks to kind of minimize the total path traveled by the nozzle. And there are some papers related to this this planning for minimizing the time to traverse on the whole pattern, versus what will be the strength of the layer. And yeah, that will be some multi-objective optimization problem. I think we may stop here, and let's come back and continue the lecture at 3 p.m. All right?
Sounds good.
Okay, let's continue our discussion on this extrusion-based systems. So to control the extrusion, there are a few different factors. One is the pressure, as we mentioned, right? And temperature. How the temperature melt, how the heat melt the material, that definitely will affect the extrusion. Also, what material you are talking about? So ABS and and PLA will definitely be different. Also, the gravity, other factors, as we mentioned, if the room temperature it will be too different with the heating temperature, that could be some different patterns or different quality of the patterns generated. And so for the support materials, as you can see, basically all these features, again, need to be supported, right? These are quite similar to what we discussed the last class. And so for some of the fused deposition printers, you can see many materials they could be can be used for these machines like ABS and like polycarbonate and so on and so forth, right? And they usually use the filament as the building materials. And some of them could achieve really high accuracy like the one shown here, right? And but still compared to other like stereolithography or those laser-based, the surface finishing is still quite low, quite rough. And the building speed is low because it will scan a pattern for each layer, right? And here shows some generated parts using the fused deposition modeling. And okay, there's a question. Oh, slide 22, okay. Oh, okay. Oh, the general, I would say on this slides, there not much information about the general characteristic of fused deposition modeling. But in the, maximum part size. Well, that's really, that really depends. For example, in Oak Ridge, you have the one can print a car, right? So that's a meter level printer. But most of the part can most of the printer can only print something like at most this, right? So but it's in the for the one at Oak Ridge, that's totally different story. So I would say right now for fused deposition modeling, the range is quite wide. And in terms of other characteristic, I would say in the previous slides, I mentioned how it works. What's the basic concept for the fused deposition modeling? And almost all the machines, no matter it's big or small, it's high end or consumer level, they pretty much share all these features. Okay, all right. Okay, let's move on. And here's another high-end machine. And as you can see, in this one, it has a room for the printing. So it might have better control on the temperature, on the thermal control. And that's why those high-end machines usually generate parts with better surface finish with high accuracy, and their reliability is much higher because they are carefully designed. All the mechanisms for fitting, all the mechanism for the extrusion, they're much better than those consumer level ones. And in my experience, I used to have a module machine from the Stratasys, and I have another Ultimaker machine. When I use the two machine, because the module one is kind of a pretty old version, so you can tell the surface finishing is pretty rough, right? But in terms of stability, definitely module is much better than those. Even Ultimaker is pretty good, but still it's more reliable using module. And well, that is the differences between those. Because module used to be quite expensive at that time when it first came up, and that is developed by the kind of one of the big the giant company Stratasys, and it's much more reliable and it's better designed, and well, that's why we still need these high-end machines, not just the consumer level ones. All right, but definitely we could have some consumer level ones like these do-it-yourself machines. Basically, these are pretty cheap and very easy to use. All right, I will introduce these two work later on. So here shows some nozzle head, and you can see it has all different parameters, right? It has the different lengths. I mean, for the length, I would say it's quite standard, but the most customized part will be the size of this nozzle head, right? So it will affect the extrusion a lot, because the smaller size you will give you less material extruded, and it will slow down the extrusion. But at the same time, the feature size will be smaller, and in general, the printed geometric accuracy will be higher. So that's why there are different nozzles with different size, and people can utilize them according to different applications, different requirements. All right. Actually, there are some students ask me a question when I first showed them this figure last semester. They asked me how these different size, all the different size related to the surface quality of the printing. Can you? I mean, he asked me whether there's some model beneath this or not. I mean, I told him, sorry, no. There actually only some empirical rules, and there's some paper talking about it. And but most of those FDM manufacturer, they keep it as a secret, because these rules only work for their machine, because the size of this nozzle will work together with other factors, which will affect the surface quality of the printing. So those manufacturers, these companies, they test on their platform, and they test this size with other hardware as well as their G-code setup. And it turns out it becomes a case-by-case situation, and it requires a lot of tedious work, right? So I would say there's still a long way to go for the standard standardization of a fuse deposition modeling machine. And I think the most, I mean, it has the biggest chance to standardize fuse deposition modeling because its patent has expired, right? So there are already some open source machine like Ultimaker and other like those RepCap and so on and so forth. But still, I didn't see the standardization happening. Okay. Maybe that could be a good direction to pursue. All right. Let's move on. Another thing is material, right? The FDM can take different those thermoplastic materials. The most commonly used one are the PLA and ABS. But this figure summarizes the properties for different materials in terms of ease of printing, visual quality, max stress, elongation at break, impact resistance, layer adhesion, and heat resistance, and so on and so forth. But it's kind of you have to again to balance. Sometimes you just want to make your printing really easy. Then probably you should choose PLA, right? But sometimes you want to have some good mechanical or chemical properties, right? So such as the maximum stress, and then you need the polycarbonate. But it's not that easy to print. You will meet a lot of problems when printed, and but that's the price you have to pay according to the application. And there's no single material which fulfill all the good properties. So there's no easy way to choose them. And you have to choose it case by case. And sometimes you have to go through those painful setup of the parameters and do some testing. Even for the most easy to use ones like Ultimaker or like MakeBot, when I first purchased them and put it in the lab, it still take me, I would say 1 week or two, yeah, something like that, to play with all the setup. Even only those simplest one. That means through their software or through their control panel, there's some kind of pop-up windows, some values you could specify. You don't need to input value, you just need to select some options, but still to test all the combinations, whether I should heat up the platform to 40 degrees or 100 degrees, and what is the fitting rate to use for ABS or for PLA. All these different combinations, it takes me a lot of time to get it work. Actually, to be honest, my first Ultimaker 3 printing is failed. I don't know why, because I mean, at that time I don't know why, but it turns out I didn't heat up the platform, and the bonding between the first few layers with the platform is not good if you do not heat it up. And turns out the printed part slide on the platform, and it ruined the whole printing process. So all these things, material, the setup, the temperature, and so on and so forth, you need to take care during the printing process. All right, and for the more details of which material has which good mechanical properties, and you can check this this figure later for your reference. All right. Oh, I like to talk this kind of aspects of FDM. So as you can see, there are different types of fuse deposition modeling printers, and the way to differentiate them is the degree of freedoms or the motion used for these systems. So this Ultimaker 2, this one is the one we mentioned in the previous slides. Basically, when doing the printing, you have to first level your nozzle in Z direction, right? And then it has a plotting bed, and the nozzle move in the XY plane at this level, and that's how it works. But it could have some delta fuse deposition printing, and I will show you the videos, and you can tell what is the difference. And after we going through the videos, we could have some little discussion on it, and that is I think it's very important for the future direction of fuse deposition modeling, because you all know I'm supporting for the multi-directional, multi-degree freedom, multi-process 3D printing. So it's kind of I really like to no, let me share my video first. Okay. Redo it. I think I didn't share the audio to you guys. Okay. All right. So as you can see in this printing process, it's not a purely 3D motion there, because when you want to access any 3D points in the printing space, you have to level your Z in the Z axis, right? So the nozzle will go back to the home position and then move to certain Z level, and then move in the X, Y plane to access the certain 3D position. So that is so-called the Cartesian fuse deposition modeling, and it is 2.5D. But there are some delta mechanism-based fuse deposition modeling process, which allows a purely 3D access. And let's check how it works. Okay, let me share the screen to you.
So what is a 3D printer? Well, this is a 3D printer, and so is this, and this one, and this one, and also this one, and this is a 3D printer, and so is this, and this, and this, and these as well. Okay, one of those was a transformer, but you get the idea. 3D printers come in all shapes and sizes, but for today's video, we're going to be talking about Delta printers. In this case, the Kossel Mini, designed by this guy and named after this fine-looking gentleman. The Kossel Mini is an FDM printer, or Fusion Deposition Modeling. Let's take a look how it works. First, you start with a 3D model designed on the computer. In this case, we're going to be printing some physics-anonymous keychains. If you don't know to something more detailed video about and starts heating the hot end. Then the raw material, in this case PLA filament, is pulled off the spool by the extruder motor and sent down a tube to the extruder. The extruder melts the filament and pushes it out this nozzle. The print head moves by the computer, drawing the shape for each layer of the object. Most FDM printers work in a similar way, but the Delta printer has a few key advantages. You may have noticed the Delta doesn't have any motors attached to the print head. Instead, they're hidden down here at the bottom of the printer. This is a big advantage to the Delta design. Some of the heaviest parts in a 3D printer are the motors, and by keeping them static, the print head can move much faster with less chance of mechanical parts flexing due to shifts in momentum. Let's look at how the printer moves the print head left, right, up, down, forward, and backward. Let's simplify the design a little by taking out one of the arms so it's easier to see. You can now see if I move one of the carriages up and down, the print head moves left or right. You may have also noticed the print head moves up and down slightly as well. This would be pretty bad if we didn't have a way to keep the printer head at a specific height. Luckily, by also moving the other carriage at the same time in the opposite direction, we can move only in the direction desired. This seems simple enough, but the 3D printer has to look at each position it moves to and figure out what position the carriages have to be in to get to that position. This is called inverse kinematics, and it's one of the reasons Delta printers aren't more popular. Because the 3D printer has to make this calculation hundreds of times a second, you need a faster processor than you might with a traditional Cartesian printer. But lucky for us, processing power is cheap these days. Delta printers can also be a bit hard to set up because the printer's computer needs to know the exact shape of the 3D printer. This includes measurements like the arm length and the distance between carriages. But once everything is set up correctly, the Delta is one of the faster and more reliable printers out there. Now we can add the third carriage back in, add some ball joints to give us a little more freedom of movement, and that's it. That's how a Delta 3D printer works. Alright guys, that's going to do it for this week. I hope you enjoyed it. A little bit different than what we normally do, but it's been fun. If you liked what you saw and you want to see more...
Alright. I think right now you know what is a Delta printer is, right? So as you can see in the video, the guy tried to drag the printing head. And you can see it can directly move, the printing head can directly move from one point to another without going through the back into home and then level to certain Z position and then move in the XY plane. So it has much more flexibility, and as a result, you can see how fast it is compared to the original Cartesian FDM 3D printer. And also there are other degree freedoms are utilized for a fused deposition modeling system, such as this polar FDM 3D printer. And let's check this as well. So you can see for the same goal, by that deposition modeling system, they are all different designs with all different degree freedoms utilized. And you can see how fascinating it is. All right.
By that, you put it on. See there, we got that blue skull there? Yeah. Oh, yeah.
Our printer is prints on polar coordinates instead of Cartesian coordinates, and because of that it simplifies the mechanics tremendously and allows us to print a very large print area, up to 300 cubic inches. The mechanics are extremely simple, and the printer is only 10 pounds.
Less moving parts?
This is the maximum we can print, which is 300 cubic inches. The printer is only 10 pounds, so it's very, very simple, very rugged.
Goes in that rock shop. Look at the stuff.
Again?
No, this is yesterday.
It's mechanically, it's very simple. The coordinates instead of Cartesian, and drastically, it's just 10 pounds. It's just real solid, real compact.
So as you can see in this kind of polar fuse deposition systems, instead of those Cartesian, in the motion in the Cartesian coordinate system, they map the whole process into the polar systems. So there will be a rotational motion on the platform, and in the Z direction, there's an extrusion, right? So you can see it's much simpler setup in terms of the mechanical mechanisms. And also, because it does not require so many mechanisms, and that reduces the weight a lot. But still, you can see the surface roughness or surface finishing of this seems not as good as the Cartesian ones. Well, that's the price you have to pay. And the last one is a robot arm-based fuse deposition modeling. And let's take a look at this one. And after I showed the last video, we can have some discussion on this. And it will relate it to your homework, because one of the questions asking you about this different degree freedoms for fuse deposition modeling. And yeah, let me share it. All right. Okay. So as you can see in this setup, a robot manipulator take place of the nozzle. I mean, take place of those machines, and you can see how flexible it is. It has all 6-degree freedoms motion over there, and if the robot is mobile, means it can move. So you can imagine how large the object it can print, right? And actually, there are some researchers, they are working on those mobile 3D printer, meaning they have a printing robot, and that robot can move. And each of the robots can print certain portion of a big object. And after printing, each of the portion can be assembled together and form an even big ones. So something like buildings or even a bridge can be printed using this kind of mobile printing robot. All right, so I would like to hear from you about your thoughts on all the different degree freedoms used for realizing a fused deposition printing, and as well as what do you think that will be the future for this kind of fused deposition modeling? You can either type or use your microphone. That's fine. Anyone want to share some idea? Can you guys speak?
Speaking's not my problem. Thinking
okay.
independently is mine.
Okay, good. Okay, so Preston is talking about cylindrical coordinate systems for our project. All right. Okay, Michael mentioned how does the delta do on accuracy? Well, that's a good question. Let me answer Michael's question, and you guys can also join the discussion. Actually, the delta ones has less accuracy than the Cartesian one. The thing is, to control the accuracy of the motion, precision of the motion in a purely 3-dimensional is not as easy as the one for the Cartesian fused deposition modeling. And that's why, although you could have better efficiency, but you lose certain accuracy. But still, if you keep on increasing the control of the motor for the delta systems, I think at some point the accuracy could be improved a lot. Actually, I have one delta, one Cartesian in my lab, so I used the same model to test the two, and turns out definitely Cartesian ones, the Altimeter 3 gives much better surface finishing, but the time is kind of crazy, 2 or 3 times slower than a delta one. So it really depends on what kind of application we're looking at. Well, that's a really hard question to see a binary yes or answer like yes or no, right? Yeah. Also, okay, so Preston mentioned we are looking at cylindrical coordinate systems for our project. Well, I suggest you definitely need to look at those polar-based systems because, yeah, you have some follow-up. Yeah, by using polar or cylindrical, can you increase your overall surface finish by changing the slicer algorithms? But again, the slicing algorithm, I don't exactly know what you're talking about the slicing algorithms. If it's still planar slicing algorithms, well, I think that could be quite similar. But if you are talking about some more like curved slicing or other ones, I don't know. I really don't know how it could be improved or not. Yeah. And Clay mentioned the robot arm is very impressive, but Polar seems much more accessible to general use. Yeah, I agree. The robot, another thing for robot is kind of, you have to think about the cost, right? So that's why those robots, for the robot-based ones, I would say the most convincing application will be the ones to print large objects, right? If you have a large object, then the robot has some beneficial. And it has much more degree freedoms. It is mobile. You can move, you can print the part and assemble them together. And that requires other automation. And the robot arm can not only do the printing, but also do the assembly automatically. And that could be a good direction for those robot arm-based printing. Also, for some, as I mentioned in last class, the like the metal cladding based printing, it already has multiple degree freedoms. So how about we utilize them, right? Like to do some non-planar layers and do some advanced planning algorithms for dividing the part into several different portions and merge them together, or to find some good printing direction to avoid printing this support material, and so on and so forth. So I can see other, these are also a good direction to think about. Okay, also this is Matt, right? Yeah, this is Matt. Yeah, Matt mentioned, I think the 6 degree freedom robots would have the most utility, but issue like heat management, exactly, and our material need to catch up to before it can do any engineering load bearing application. Yeah, I think that's a good point to think about. The heat management becomes much more difficult because you are really talking about those large size objects, right? And in an open environment. So like the application like such as building or bridge, right? It's really large and in an open environment. Also, the requirement for the mechanical property for the load bearing, it has higher standards because it related to the safety, right? For the people's safety. So that's really high requirement for this kind of printing. Because for other applications, if you just use like a plastic, or you just print some toy, there's nothing to do with people's safety. If it's not that strong, that's fine. But for those bridge or building, you need to think about it. So, okay, also Matt mentioned one big problem I see with Delta printer is small building area since your joints are inwards. Yeah, that could be a good, that's indeed a good a limitation, because the space is restricted by the setup of those mechanisms. You cannot go beyond the top of the top place for the mechanisms. Yep. Okay. Any other thoughts? Anything regarding this these different types of fused deposition modeling could be brought out for discussion? I think I won't give you more content in today's lecture. We can just openly discuss whatever you want for today's lecture, and other stuffs related to your project, related to the process, fuse deposition modeling, or so on and so forth. So basically, after this class, I will post the assignment. There will be 2 questions, one related to the fused deposition modeling printer, another one is in general for the understanding of additive manufacturing. So yeah. Actually, maybe I can give you some. Okay, will you be able to post that today? Yeah, I definitely I will. And the due time I set up will be 2 weeks later. I don't remember the time. It's July 12th or something. Yeah, you have a lot of time because next week you will have the Independence Day vacation. So I just let you guys to have a good vacation. So you don't so you don't need to hand in your homework at that time. But definitely 2 weeks, July 12th something. Yeah, if my memory is correct. Yeah, I will post it today, just after the class, because I think because one problem is related to this different types of fused deposition modeling printer. So I would like to have the class first and then post the questions. Right? And you can hand in your your homework by using this system. I mean the iLearn system. You can. I will open up a session. You just submit the homework. So be sure to know how to submit it. I can help you if you have problem. I can help you either by email or I can teach you how to use it next class on next Tuesday. All right. Also, I email you just right before the class about the groups, project groups. Please let me know whether you form a group or not. And if you have difficulty, I will help you to find some group mates, right? Such that you could start work on the idea. All right. Till now, I have Kristen, Scott, and Tommy emailed me back about the groups, and I know Michael, not Michael, Kevin, and I don't remember who else. Dog and who and the other 2, they also form a group. But please just give me the names. Yeah. I have it. Good. Robert and Matt. Yeah. And then we have 7 people. So how many in total we have? We still have 2 to 3 people left. And okay, that's it. Okay, I think I have all the groups. Yeah, good. Michael, Drew, and Clay. Okay, good. Yeah, I think we have 3 groups. And as long as you have, I mean, now you have formed the groups. So please start the discussion and brainstorming with your group mates. And also you can talk to me about your ideas of the project. And I will try my best to help you to shape your project. And we can talk through emails, or when I go there at Oak Ridge, we can talk during the breaks or even during the class time. We can talk about it, because that on-set session is kind of more casual for discussion and sharing ideas. All right. Okay. Good. Yeah. Okay. So any other comments or questions? Okay. I think if you guys have no other questions, we can just stop here. And we will continue talk about the fuse deposition modeling next class, and also we will have more time to discuss on the project and whatever you want to talk related to this class. All right? Okay. Thank you. Thank you for your attention.
Thank you.
All right. Let me just stop the sharing and stop the recording.